So in this tutorial we are going to study the graph data structure. We have already discussed a lot of data structures. At this moment we have studied the linked list, the double linked list, stacks, queues, etc. One basic thing that you will observe in all those data structures is that you are storing data which does not have any relationship. So they are basically isolated data. So in some practical I will just show you some practical examples where we have to store the data which have some relationships between them. So I will use the example of how Facebook uses the friend request mechanism, and it uses the graph data structure to actually store the relationships among two profiles. So before that, let's focus on the graph. So graph is basically a data structure. So I'm going to write here that graph is a data structure, and it has two components. So graph is a data structure. So the two components of graph are: number one, the graph contains a finite set of vertices, also called as nodes. So finite set of vertices called as nodes. So nodes are basically the vertices which contains the actual data. For example, you can store integers in them. We have studied about nodes. So graph does have nodes, and the second component of graph is finite set of ordered pair. So I'm going to write a finite set of ordered pair of the form u comma v, called as edge. So here I've defined another component of the graph which is known as edge, and it is a finite set of ordered pair, which simply means that edge is used to connect two nodes, and these nodes form a pair. For example, let's say you have a node with integer 1 and you have another node with integer 5. So these two are basically nodes, but a graph should contain both of these components. So these are the nodes, and if you will draw an edge is simply a line, a straight line. So this is basically an edge, and you can see that this is an ordered pair of form 1 comma 5. So this is basically the meaning of edge. So the pair is ordered because the u comma v. So I'm going to write here pair is ordered because the set, or you can say the pair u comma v, is not equal to v comma u. So in this case 1 comma 5 and 5 comma 1, so these are the two pairs that we can make from this graph. So let's suppose this is a graph with two nodes 1 comma 5 and an edge that is connecting between the graph. So there are basically two types of graphs. One is the directed graph and another one is the undirected graph. So basically directed means that the edge, so this is an edge, so an edge that is connecting the both the nodes, the edge is directing, or you can say the edge has a direction. So let's suppose we want to say that this is number 1 and this is number 5, and number 1 is the friend of 5. So I'm going to write a direction here that 1 is a friend of 5. So this means that the ordered pair 1 comma 5 is existing, but we can say that 5 does not consider 1 as his friend. This can also happen. So 5 comma 1 does not exist. So this means that the relationship can be directed from one node to the another node, but the inverse is not necessarily equal in case of a directed graph. In case of undirected, we're just going to say that 1 comma 5 is basically equal to 5 comma 1 because there is no such direction. So the next thing that I want to discuss here is that we can represent graphs. So basically this is the next topic, representation of graphs. So now we have seen what exactly a graph is, but we want to know how can we represent this graph in our program so that we can actually use them in our program. So there are basically two ways to represent graphs. Number one is using an adjacency matrix. And number two is the adjacency list. So we have already studied about linked list data structure, and we are going to use a familiar you can say structure to represent the graph. So let's study how we can represent a graph in an adjacency matrix. So we know what exactly a matrix is. So first of all, what I'm just going to do is I'm going to take an example of a graph. So let's suppose we have a graph like this with node 0, with node 1, then 2 and 3, then 4. So let's suppose these are the 4 nodes of this graph. And now what I'm just going to do is I'm going to connect these graphs using edges. And I will consider that this graph is an undirected graph. So I'm not going to show any direction using an arrow. So let's take an example of this graph where these are some of the nodes which are connected to each other. So let's suppose 0 and 3 are also connected. So now what I have to do is I will have to represent this structure in a matrix. And we need, and in mathematics we have already studied what a matrix is. So this is actually a prerequisite. So what we're going to do is we're going to create a matrix with 4 since these are the 4 vertices, we are going to create a matrix of 4 by 4 length. So I will create a matrix that have 4 elements in it. Sorry, 4 into 4 means 16 boxes. So 4 by 4. So we know that the index positions of this matrices can be written like this, starting from 0, 1, 2, 3, and 0, 1, 2, 3. So basically there are 5 vertices, so I will have to draw 5 vertices. So I will extend it for one more row and column. So this matrix is a 5 into 5 matrix, and I'm just going to write all the index positions. So let's suppose we can create a two-dimensional matrix with index position 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, and similarly like this. So now what we are just going to do is if two nodes are connected, or I should say they are adjacent, connected slash they are adjacent. So I'm going to mark that position in the matrix as 1. So let's take an example of 0, 1. So you can see that in the position 0, 1, since 0 is connected to 1, I'm going to write 1 in this box. So basically I will store the position of array 0, 1 equals 1. So 0, 0, since there are no cycles are basically let's suppose we want to say that 1 is a friend of himself. So I can draw a relationship like this. So this is basically a circle, a cycle. So what we can do is since 0 is not connected to 0, since there are no cycle, we can mark 0, 0 as this. Similarly 1, 1 is also 0, 2, 2 is also 0, 3, 3 is 0, and 4, 4 is also 0. So now we know that 0, 1 is 1, and since 1 is also connected to 0, we are going to mark the position 1, 0 as 1. 2 is connected, so now let's pick up the node 2. 2 is connected to 0, so I will mark it as 1. 2 is connected to 3, so I will mark 2, 3 as 1. So now since all the adjacent elements have been filled, now I will pick up another node which is 3. So 3 is connected to 0, so I will mark it as 1. 3 is connected to 1, so I will mark it as 1. 3 is also connected to 2, so again 1. Then 3 is connected to 4, again 1. Now we will pick the element 4. 4 is connected to 1, so I will write here 1. 4 is not directly connected to 0, so I will mark 0 here. 4 is also not connected to 2, so again a 0. Similarly 4, 3 is 1. So 2, 1, since it is not connected, we are going to mark it as 0. 1, 2, again 0. 1, 3 is 1. 1, 4 is also 1. 2, 4 is 0. Then 0, 2 is 1. And similarly 0, 3 is also 1 because 0 and 3 are also connected. 0, 4 is 0. So this is how we are going to represent this graph in the form of this matrix. And there are basically advantages and disadvantages in using matrix. So number one is the advantage. So advantage of using a matrix is that we can easily delete a particular relationship between two nodes. For example, let's say I want to delete the relationship, or I want to remove the relationship between 1 and 3, or you can say I want to mark you can say I want to unfriend 3 wants to unfriend 1, so he does not want to remain connected with 1. So removing an edge takes only big O of 1 time complexity. So let's suppose I want to remove the connection between 1 and 3. So what I am just going to do is I'm going to mark the position 1 comma 3 as 0. So this will be marked as 0 instead of 1, and 3 comma 1, which is here, I will again mark this as 0. So it takes only one axis, only this axis, to remove the edge. So this is a main advantage of using an adjacency matrix. You can actually remove a relationship between two nodes. So let's take the example of Facebook. So let's suppose we take an example of Facebook. So let's suppose there are two profiles, you and your friend, and so you have some data in your profile and your friend also has some data in your profile. So let's suppose you are number 1 and your friend is stored as with number 2 identity. So now what you are going to do is let's suppose 1 sends a friend request to 2. So we are going to connect 1 with 2 using this edge. Now let's suppose number 2 does not want to accept the friend request. So we are going to just mark the position array 1 comma 2 as 0. So it just takes big O of 1 time to remove the friend request. So a very decent time complexity. So now let's say 2 wants to accept the friend request of 1. That means 2 wants to connect to 1. So the connection or you can say the relationship is 1 to 2 and also from 2 to 1. So once both are connected, both can view profiles of each other. Since everyone is a friend of or everyone can view their own profile, we are going to create a cycle like this. So one can view its own cycle, so it has a relationship with himself, and similarly 2 can also have relationship with itself. So Facebook uses graph data structure, and a lot of companies also uses graph data structures, since you can actually draw the relationship between 2 and more nodes using the edges. And one more application of the graph data structure is that it can be used to find the shortest path between two nodes. So let's suppose I want to find the minimum distance taken by a person from 0 to 4. So let's suppose 4 is the destination. So one more thing that I want to tell you is that each edge can hold some value, or you can also say weight is the same thing. So let's suppose the distance between 0 position and 1 position is 15 meters. So I can mark this edge as 15 meters. Or let's suppose we say that the time taken by this person to move from 0 to 1 position is 5 seconds. So I can also mark it as 5 seconds, which will be the weight or the value of the edge. And so this is also useful if you want to find the shortest path, and we are going to study the Dijkstra's shortest path algorithm later on. Shortest path algorithm, which is very useful in a lot of places, which are used in a lot of applications. So basically we have studied what a graph looks like and how you can represent it in the form of a matrix. So now let us discuss how you can represent this graph in an adjacency list. So one more thing, I want to discuss the disadvantage of using a matrix. So disadvantage is the space complexity. So let's suppose there are 5 nodes like this. So you can see that most of the space is if you're creating an matrix of 5 into 5 length, each and each entry holds an integer value. So let's suppose integer takes 2 bytes. So you will create 5 into 5, 25 into 2, so 50 bytes are allocated for this matrix, and you can see most of the values, or you can say the most of the entries or most of the memory is not occupied. They are assigned as 0. So you can see that there are a lot of zeros than 1. So a lot of space is wasted. And we have also seen that this same example in case of an array and a list. In array you will have to allocate it first, and even if you do not want to fill it with all the data, then a lot of space is wasted. So this is known as a sparse matrix, and sparse matrix means that it is most of the space is not acquired, so that's why it's sparse matrix. So this disadvantage, we can remove this disadvantage by using an adjacency list. So let's see how we can create an adjacency list to remove this flaw. So what I'm just going to do is, we know that there are 5 nodes marked from 0 to 4, so I'm going to create 4 small boxes like this, and I will mark each of these boxes from 0 to 4 positions. So 0, 1, 2, 3 and 4 is also there, so let me just mark 4 here. So what we're just going to do is, we're going to create a pointer, as we know that we use the next pointer in case of a linked list. We're going to use linked list to actually represent this graph, and adjacency means that we are considering the adjacent elements. So you can see here the element should be adjacent. So let's move to 0 node. So we know that the 0th node is connected to 1. So what I'm just going to do here is, I will create a node that has data stored in it with the next value. So let's suppose the data is 1. So 0 is connected to 1. That means that we can just use the next pointer of 0 to reach 1, and this next pointer is of 1. We can make it null, but we know that 0 has some more adjacent elements in it. So the adjacent element of 0 is 2 also. So what I'm just going to do is, I will create another node like this with next pointer, and since 0 is also connected to 3, I'm going to create another node with its next pointer like this. So this is 2 and this is 3. So we are just going to show that 0 is adjacent to 1, and we will link all the nodes which are adjacent to this 0th node using the next pointer like this. And since there are no more adjacent matrices left, we are going to make it as null. So you can see in this case that a lot of space has not been consumed. As you can see, in case of matrices, a lot of space was left. In case of linked list, we're just going to use the pointers, and we are storing only those nodes which are connected to this node. So we're going to do the same with all of the nodes. We are going to create a list, and let's suppose 1 is the node that we are going to pick up, and we know that 1 is connected to 0, 3, 4. So we will create 0, 3 and 4. Order does not matter in case of an undirected graph. So it will go like this. And similarly, you will do the same thing with the nodes 2, 3 and 4. So the main advantage that I'm going to write here, the main advantage of using a linked list, or you can say an adjacency list, is space complexity. So space is lesser, so I'm writing it like this. So if you have some space related issues, so let's suppose Facebook has billions of users, so you cannot create a 1 billion by 1 billion matrix, and we know that most of them are not connected to each other. So what we are just going to do is we are going to use adjacency list in that case. But there is a disadvantage in using an adjacency list. It takes more time to delete a particular relationship between the nodes. So let's say we want to delete the relationship between 2 and 3. We do not want these two persons to remain friends. So what we'll have to do is we will have to move to this pointer 0, and then we will have to traverse along all the entries till we reach 3. So this is going to take big O of n time. So this is the basic disadvantage. So let's suppose 0 has hundreds of friends, and they are connected to each other. So let's suppose I want to delete the relationship between 0 and 100. So you will have to reach to the 100 position, which will take big O of n, which is big O of 100. That means 100 will take to reach that position. So this is the basic disadvantage. We can remove this disadvantage by using the concept of skip list, but I will discuss the skip list data structure later on. But this is exactly how a graph looks like. In the next two tutorials, we are going to study how we can search for a particular node in the graph. So basically we are going to see these two strategies of searching, which is the breadth first search. So these are two strategies that we are going to use in case of a graph: depth first search and the breadth first search, which are really very important. So first you will have to do this, and then we will move on to the shortest path algorithm, the Dijkstra's shortest path algorithm. So thanks for watching.